Professor Zawil, let me first congratulate you to this year's Nobel Prize in Chemistry for your pioneering work on femtosecond spectroscopy. Would you like to tell how you got started in this interesting field that you have developed?
Well, Professor Forsen, everybody thinks sometimes that science is done as a master plan, and that somebody like me came from Mars and figured out everything and so on, but that's really not the way it works. We started at Caltech asking very simple questions. How do we understand the molecular dynamics or the dynamics of molecules, the motions and so on of molecules, but in a coherent fashion? These molecules, there are millions and billions of them in the sample that we want to study, and they are all at random, and there are no relationship among them, and we would like to just order them somehow so they all can behave at the end as if they are a single molecule trajectory. So in the beginning, we were trying to develop new laser techniques to see how these molecules, if we prepare them coherently and we study them in a coherent fashion, that then we can learn about the intrinsic processes, such as how does the energy move in the molecules, how molecules change their orientation, and so on. So we did some of the analogs of the powerful nuclear magnetic resonance techniques, which you are very familiar with, and used coherent pulses and pulse sequences. But then around 1980, I was asking the question, can we do the same thing in a single isolated molecule? Completely isolated from the rest of the world. The environment is not there. So the question of using then a combination of molecular beams and ultra-fast lasers came to mind, and we start to initiate this research area, which I had no idea what's involved in terms of molecular beams, but we had, my students and I had to get into this area. And fundamentally, we're thinking about if we now excite an isolated molecule, no collision, no perturbations, that if we excite certain vibrational mode in the molecule, how would the energy move into all the other modes in the molecule? There are many theories and many ideas of how this moves. And the typical one, it goes back to your Arrhenius, namely that the energy will go in a random way. But to the pleasant surprise of all of us is that the energy was not randomizing on the short time scale. We found actually that the energy goes from this mode to another modes and come back, even though we have millions. We have a whole forest of modes in the molecule, but the molecule is behaving very selectively and coherently, and the molecules are very complex that we were studying. And that was really the beginning of femtochemistry science, because it immediately indicated to us that if we can excite molecules and initiate this in molecules on a very short time scale, prior to their vibrational and rotational and scrambling of energy and everything, we should be seeing a whole new world of ordered coherence in them. And by 87, we made what's the Nobel citation called a breakthrough, namely that by so doing, we were able to see the motions of the real atoms inside the molecules and with atomic scale resolution of the dynamics.
Thank you.
Professor Zawil, the resolution at which one can study chemical reactions has been constantly decreasing over the past century. Do you think it will be possible, or is it even necessary to go further? Might there in the future be a field of autochemistry?
Yes. This is a legitimate question, actually, because I wrote something about this. But the Nobel citation, which was very well written, actually, pointed out that this is the end of the, if you like, the race against time. The reason for that, it's fundamental. It is not that we have to keep shortening the time. It turns out all molecular and biological systems have speeds of the atoms move inside them. The fastest possible speeds are determined by their molecular vibrations. And this speed is about 1 kilometer per second, 1,000 meters per second, which means that if you have femtosecond time resolution, or 10 to the minus 15 or 10 minus 14 second, you have a distance resolution of about 1/10 of an angstrom. That means really that you are now frozen all the chemical or biological structures on that time scale. You can't do any better. Where I think the auto or sub-femtosecond is going to be important, and I suggested this in one review article, would be to go into the motion of the electrons. So who knows? It may be that we will see one day how we can localize also the electron, just like we did with the nuclei. But I think that will be beyond the realm of chemistry and biology. You will be now addressing issues in physics, looking at semiconductors and high energy physics and so on. But that's, I don't want to commit myself and then proven to be wrong later, but that's basically what I think about it at this point.
How do you see future directions in the studies of chemical and biological phenomena with time resolutions of the order of femtoseconds? Would it be possible to make sort of snapshots, X-ray diffraction,
yes.
femtosecond
yes.
timescales,
yes.
or electron diffraction? How
yes.
do you see the future, let's say the next 10, 15, 20 years?
Yes, I'm glad you asked this question, Professor Forsen, because I thought in my lecture I pointed out, on my Nobel lectures I pointed out that I was delighted that the Swedish Academy of Sciences did not quote anything about my current work right now. Because the current work that my group is focusing on is actually both the time-resolved electrons and possibly X-rays to be able to get the architecture of these molecules, the molecular structures themselves, of very complex biological systems. That's the ultimate goal. We have succeeded so far to do this diffraction type experiment on smaller molecules and to look at intermediate transit structure. But you can imagine the power of this, maybe in 10 years, when we are able to look, say, at the intermediates of proteins process, or the motions of some of the DNA structures that we are interested in, the effect of solvation. Does the hydrophobic forces play a fundamental role in the process of folding? There's just numerous questions that we'd like to ask, and we really have to look at these snapshots at early times.
Femtochemistry provides very strong possibilities for new drugs. Do you think it will ever be possible to study at that level in a living cell, to perhaps study enzyme reactions?
Well, that will be really a fantastic advance. Of course, the difficulty usually we get into this at this point in time is that in the cell there are the medium itself and the water and so on. But one advantage of the femtosecond time resolution, and we demonstrated this in a number of studies, is that even in liquid type environment, same coherence I was talking about and the motions that we're seeing, we can actually isolate because the perturbation from the solvent is not turned on yet on that time scale. So some people have started to use actually femtosecond methods to image processes in cells. There has been work on DNA. In fact, I'm involved in this with my colleagues at Caltech in looking at the transport of electrons in DNA. A lot of work has been done on proteins, including cytochrome oxidase and others. So you will see a variety of applications in the coming years.
I know that you have a strong desire to promote science and help young scientists in your country of birth, Egypt. What are your plans in this direction? And can you tell something about that?
Yeah, I do feel quite strongly about this, that probably one of the things that I'm fortunate at this age now to get the Nobel Prize is to really use part of it to help the young people get excited about science. In the States, in the world at large, but also with particular focus on Egypt, because I came from Egypt and I owe Egypt a lot to where I am now. And I do feel that there are tremendous amount of talent in Egypt, human resources. Human resources are just tremendous in Egypt. But we need the science base. They need the correct science base, how to get these people to interact with each other. When I give a lecture in Egypt, there are thousands of people in the lecture hall. So obviously they would like to go to science and they would love to do science. But you really have to get the correct science base in order for them to interact. So we are hoping to have maybe little Caltech, maybe little Lund, that just to start something there that really both the Egyptians and colleagues from the Western world and so on can interact with each other, get the students to exchange and do science at the frontiers.
You think the Nobel Prize will help you in this respect?
I think the Nobel Prize helps for a number of reasons. Number one, if I can be frank, these people will feel by getting a Nobel Prize that I'm one of them, that it is possible to contribute on the world map of science and technology. That's not only in the hands of the Swedes and the Americans and the British and so on, that they could, if they work hard and they have the abilities and so on, they can achieve even on the highest level. And the other thing also, which I'm hoping for, is that the government in Egypt is willing and interested in promoting science and technology, and this is an ideal time now to be able to do something.
Are there certain fields of science which you think might be especially well suited to young scientists in Egypt?
I think in Egypt and all over the world, you know, David, there are many books I read talking about the end of science. There are many books have. And I think this is quite naive, actually, because we all just try to uncover something. But the universe at large is full of questions that we still don't know anything about. And there will be always young people, brilliant, who are going to make new discoveries. I mean, if you think in 1999, now this is the ending year of this millennium, and you just think about the world of the very small, thinking about manipulating the atoms and the molecules, think about the whole world of biological complex sciences. We still don't understand why a protein folds the way it does.
Yes.
Huh? I mean, it's an amazing thing. So all of this is open up. You go to the very big, you go to astronomy. We still don't understand how the Big Bang and evolving all the way to the human species and so on. So all of this is going to be very exciting to the new people. But for me to sit down here, even as a Nobel laureate, and make a prediction about which science, I think that would be a mistake.
Scientists are supposed to be creative, and surely they certainly are, and you are a most creative man. What are your best creative moments? Is it in the shower, when you are listening to music, or in the early mornings? Can you say something about that?
Yeah, it's a crazy, actually, moments. You just never know. Well, one of the things I enjoy most is to be left alone with a book. I am not one of the new media experts working all the time with my computers and PowerPoints and things of that sort. So I'm an old-fashioned still in this regard. But this is really these are the moments where I really can be creative, if I am. To be left alone with just a book and piece of paper and to be thinking. And I think actually one of the messages to the young people, building on David's question, is the internet and all this wonderful thing we have. These are not thinking machines. These are information gathering. But you should have some time to think, and that's very important.
Nobel laureates usually complain that getting the Nobel Prize perturbs their life infinitely. And how do you try to get away from, to find your sort of precious moment of creativity in the future?
Well, I tell you a story, and I tell you how I'm trying to do it. When they called me with the Nobel call from the Secretary General of the Swedish Academy, it was 20 minutes to 6, and he said, well, Dr. Zawil, I hope I'm not disturbing you, but I am the Secretary General of the Swedish Academy. And of course, you can imagine I was frozen in time when he said that. But then he made a very famous statement, something to the effect that this is the last 20 minutes of peace of your life. And he was right. At 6 o'clock exactly, until today, I just have not had the time to be in equilibrium with myself. We receive thousands of emails and faxes and so on. But I want to really focus in doing these two things. I really would like to focus on science and the excitement of science and to help with science. So that's my intention, to focus my efforts there, and I hope I will be able to do so.
Like the previous answer regarding the internet, there's a lot of talk about information overload, that there's so much information flowing nowadays, especially with computers and things, that people get sort of too much and can't think any longer. Do you think that could be a problem for scientists, that it could eventually even become detrimental, that there's so much information that it becomes difficult to sort of concentrate on a specific area.
Yeah, I do have a concern. However, humanity has a great way of adapting, and I'm sure scientists of the future, probably after I leave this planet Earth, will have a new way of dealing with the internet. But I do have a concern in the transition period, namely that, I'll give you an example. When I was a graduate student and we get a journal, let's say in your case molecular biology or a journal of chemical physics or something, you know, we are dying to take the whole journal and find out the different areas of science. Professor Forsain is aware of many areas that's going on from physical chemistry to molecular biology. But because of the internet nowadays, people are getting more and more specialized. And so I found with my students, they don't necessarily look at journals anymore, but they print right away from the internet what's relevant to what's he doing.
Yes,
you see?
that's true.
Yeah, and then you're probably living example.
I'm guilty also.
Yeah. So there is a danger. One has to really be knowing much more because you can't be too narrow in science. So.
No. We have actually received a question from Egypt, from a student at the American University in Cairo. And he says, "Sir, addressing you, in your judgment, who was the best chemist, physicist, biologist in this millennium?" Millennium, not
Millennium,
century.
yes, not century. Well, I think that's a $1 million type question. Yeah. But I would like to tell this young person who's asking the question from the American University in Cairo, is that in science it doesn't work this way. Scientists contribute in a variety of ways. And I don't think I can single one, even including Einstein, that I can say that is the best. We don't work like the best basketball player and the best musician and so on. Science is a collective effort. I build on the efforts of a previous scientist. Others will build on the work I'm doing. And if I look at the whole scope from chemistry to biology to physics, the list is too long to mention just one, and it's not fair to the others.
Yeah. I see that our time is drawing to a close here with our 30 minutes. And I would like to thank you very much, Professor Zawil, for coming here and letting us interview you during these nice conditions. Thank you very much.
Thank you so much.